Welcome to The Explainer. If you're prepping for the MRCEM Primary, you know evidence-based medicine can feel like a huge hurdle. Well, today, we're going to fix that. We're building your go-to EBM toolkit, a high-yield cheat sheet that's going to help you nail those stats and study design questions you are guaranteed to see on the exam. So let's dive right into a scenario you've probably lived a dozen times. A patient comes in, short of breath, chest pain, a bit tachycardic. You're thinking PE, so you send off a D-dimer. The result pops up on the screen. Now what? Your next move, your whole decision-making process, it all hangs on the core EBM ideas we're about to break down. So keep this patient in mind as we go. Here's our game plan. First, we'll tackle the basics of diagnostic tests. Then, we'll get into how to evaluate treatments and size up the evidence. After that, we'll demystify some of that research jargon, and then, most importantly, we'll bring it all together and apply it right to the ED shop floor. Okay. First things first, we're starting with the single most important tool in your EBM arsenal, the one thing that almost everything else is built on, the 2x2 contingency table. Seriously, you need to know this grid inside and out. It is the foundation for pretty much every diagnostic calculation you'll ever have to do. Think of A and D as the good guys. The test got it right. But B and C, they're the villains, the false alarms, and, even worse, the misses. Getting this is absolutely key. So, sensitivity. Notice how the formula, A divided by A plus C, is all about that first column. We're only looking at the people who actually have the disease. So, sensitivity is just asking one simple question. Out of everyone who is sick, what percentage did our test successfully pick up? And specificity is just the mirror image of that. It focuses completely on the second column, the healthy people. It's asking, of all the people who don't have the disease, what percentage did our test correctly clear? It's all about weeding out those false positives. And this is where it all becomes clinically useful. Let's go back to our PE patient. A D-dimer is a classic high-sensitivity test. Its whole job is to be a wide net, to catch anyone who might possibly have the disease. And that's exactly why SNN out works. A high-sensitivity test with a negative result lets you confidently rule out the disease. Okay, let's switch gears a bit. Instead of looking down the columns, let's look across the rows, specifically that test-positive row. This gives us the positive predictive value, or PPV. This is what answers the patient's real question. Doc, the test came back positive. What's the chance I actually have this thing? You can see right away how that pesky little B cell, the false positives, can really mess with the PPV. Now for a really powerful tool, likelihood ratios. You know, their biggest advantage is that they aren't affected by how common or rare the disease is. A high positive likelihood ratio, say anything over 5 or 10, massively boosts your confidence that a positive test means your patient really has the disease. It's a real game changer. Okay, diagnosis is sorted. Now what? We have to decide on the best treatment. So let's look at the tools that tell us if a new drug or procedure is actually worth doing. So before we can get to what I think is the most useful number in all of therapeutics, we have to understand this one first. Absolute risk reduction, or ARR. The key word here is absolute. This isn't some fancy percentage. It is the real, straightforward difference in bad outcomes between the folks who got the treatment and those who didn't. It's as simple as subtracting one group's risk from the other. And here it is, the number needed to treat. It's so elegant, and it's so incredibly powerful. It tells you, straight up, how many patients you have to treat to prevent just one bad outcome. I mean, the ideal NNT is 1, right? Treat one person, prevent one bad thing. It doesn't get more clinically relevant than that. Okay, now listen up, because this is a classic exam trap. You'll see a study boasting a 50% relative risk reduction. Wow, sounds amazing, right? But you've got to dig deeper. What if the risk only went from 2% down to 1%? Yeah, that's a 50% relative reduction, but the absolute risk reduction is just 1%. And that gives you an NNT of 100. You'd have to treat 100 people to help one. All of a sudden, it's not so impressive, is it? Always, always find the NNT. So, you're reading a new study about a fancy new test or treatment. How do you actually know if you can trust it? How good is the evidence? Let's figure out how to appraise it. You've definitely seen this pyramid of evidence before. Right at the very top, you've got meta-analyses and systematic reviews. They're the king of the castle because they combine the results of lots of good studies. And way down at the bottom, expert opinion, which is basically just someone saying, because I said so. As you go up that pyramid, the evidence gets stronger and the risk of bias gets lower. All right, let's really nail the difference between these two study types because examiners love this stuff. A case control study is retrospective. It starts with a group of sick people and looks backwards in time to find what might have caused it. It's quick, but people's memories can be fuzzy. A cohort study is usually prospective. You start with a group, check their exposures, and then follow them forward in time to see who gets sick. It takes longer, but it's much, much better for figuring out cause and effect. Right, we are on the home stretch now. Let's just quickly decode some of that key statistical language you're going to find in the abstract of pretty much every paper you ever read. So when you see data that follows a normal distribution, that classic bell-shaped curve, there are a few things you have to remember. That 68-95 rule is essential, the percentage of data that falls within 1 or 2 standard deviations. And also remember this, the mean is just the average, but 1 or 2 crazy outliers can really pull it sideways. The median, that number smack in the middle, isn't affected by outliers, which often makes it a much better reflection of the data. I can almost guarantee this will come up on your exam. Here's how to think about it. A type 1 error is like being trigger happy. You get all excited and claim you found something new, but it was just a fluke. A type 2 error is the opposite. You're being blind. A real effect was staring you in the face and you just completely missed it. And here's another classic trap. Mixing up p-value and power. They are not the same thing. A small p-value, that famous less than 0.05, all it means is that your result probably didn't happen by random chance. Power is totally different. Power is about whether your study was big enough and good enough to find a real effect in the first place. An underpowered study might miss a real effect and give you a misleadingly high p-value. Okay, that was a ton of theory, I know. But so what? How does any of this actually help us when we're in the middle of a chaotic shift in the emergency department? Let's bring it all home. See, this is how it all clicks into place. We use super sensitive tools like the D-dimer or the Ottawa ankle rules for one reason, to rule things out. And the next time you see a trial for a shiny new sepsis drug, you'll know to ignore the flashy relative risk reduction and hunt for the NNT. That's what tells you the real-world impact. Voltaire had this witty line about how our job is just to keep patients entertained while nature does the healing. And hey, maybe that was true back in his day. But now, EBM gives us the tools to do way, way more. It lets us diagnose properly, intervene meaningfully, and actually know the impact we're having. So after all of that, here's the final question. The next time a new study lands on your desk, which number are you going to look for first? The p-value, which just tells you if something is statistically interesting, or the NNT, which tells you if it will actually make a difference to your patient. Answering that question, well, that's the whole point of practicing evidence-based medicine.